Okay, hi everybody. So here we are again with numerical integration. So given f, a function, and a subset of the input space, briefly describe numerical integration. Well, break that subset into pieces. And choose points on each piece Okay, and then what do we do? Compute a sum of the values f at each point, xi, weighted by volume. Okay, so that's basically it. There's a formula. You could write, you're going to sum, the weight is going to be the volume of the ith piece multiplied by the value of x, or the value of f at x sub I. And I don't know why I have all these parentheses. Sometimes parentheses are helpful. Sometimes they clutter things. These parentheses mean I'm evaluating the function f at the input x sub I, or the ith point that I chose. Okay, good, that's part A. Part B, I'll start with a picture. Approximate the integral on this subset. This is a product of sets. I'm multiplying the set. So what does this look like? So let's first draw. This is helpful notation because this is going to be a rectangle. And rectangles come up often in math. So like maybe this is 3, 2, 1, and maybe 1, 2, 3, 4. And so 0 to 4 is this interval here. 1 to 3 is this interval here. And so the multiplication of these two intervals is now going to be this rectangle right there, okay? And so I need to break it into pieces. This is A, and so I have to break it into some pieces. How about I break it like this? I can break it anyway. I needed at least 4 pieces. Good, and then let's choose some points. How about this point? Will be on this piece, the first piece, maybe this point on the second, maybe this point on the third, and this point on the fourth. Okay, and so let me just write that out. I mean, maybe I'll just say that x1 is the point 0, 2, that's x1, and a1 is from 0 to 1, product 1 to 3. So I could say a1 is 0 to 1, the interval, times the interval 1 to 3. And I could continue with that, but instead I'll just, so I could, if I wanted to, keep going. But instead I'm just going to skip right to the answer. It just says numerically approximate. Now, the function, remember f, sent a point xy to 3xy plus 2. 3xy plus 2. So I just need to evaluate this function at these 4 points in dark blue. Okay, so for example, at x1, this gets sent to 3 times 0 times 2 plus 2, which is 0 plus 2. What are my other points? This point is 1, 2. And that gets sent to 3 times 1 times 2 plus 2. Well, that's 6 plus 2 is 8, I guess. This point right here is the point 3, 2.5. Okay, and that gets sent to 3 times 2.5 plus 2, which is, okay, 9 times 2 is 18. 9 times 0.5 is 4.5. So 22.5 plus 2 is 24.5. Okay, the other one, the last point is 3 comma 1. 3 comma 1 gets sent to 3 times 3 times 1 plus 2, which is 11. Okay, so I'm almost done. Now I just need to actually compute this sum, this weighted sum. I take these values that I just computed, and I weight them by the volume of their pieces, and I add it all up. Okay, so I can do that. So the first volume, let's write volume of A1 times f of x1 plus volume of A2 times f of x2 plus, and there's two more terms. So what's volume of A1? Well, each of the pieces I chose to have volume 2. So this piece has volume 2, this piece has volume 2, because base times height is 1 times 2. The value that I computed is 2. Now the volume of this piece was 2, and the value I computed is 8. Plus now the volume of this piece is 2, and the value I computed is 24.5. Okay, 24.5. And then last, I'm going to add one more weighted sum. The weight is, again, the volume is 2 times the value, which is 11. And so that's the answer. This right here is the integral of the function f over the region A, and it's approximately this number. Okay, words, pictures, and formulas. Looks good. Let's look at my other solution. Okay, so I chose different points, and so the value of the function was different, but I chose the same pieces, so their volumes were all 2. Pretty similar.